Welcome back. Oh, I'm such a good singer. You know what I should do? Commercials for Dunkin' Donuts. I'd be really good at it. You know why? Because I love Dunkin' Donuts coffee. Is there anything better than Dunkin' Donuts coffee? Anyway, kids, here we are. Unit 1. Let's see. Let's go back to fuchsia. Oops. Unit 1. Day 3. Drei. Well, I should start teaching you guys German. Tage 3. This is going to be our notes for today. Actually, I don't know how to say the word notes in German. That's a word I just never used, right? Could you imagine walking around Germany? Could you give me those notes? No, I don't think so. Anyway, today we're going to talk about this thing called one-to-one functions. So the thing you have to remember most about this is it has to be a function before it can be a one-to-one function, right? That'd be like saying I'm a professional football player. Well, are they a football player? Now, are they a professional football player? Why would you even ask me that, right? Like if I told you, hey, I play baseball. Well, are you a professional football player? No. I could say, hey, I play football. Oh, are you a professional football player? So the idea of a one-to-one function is it has to be a function first, and then we decide whether or not it is a one-to-one function. Okay, so the definition of a one-to-one function is a function. So first and foremost, it must be a function. And what's the idea of a function is, remember, for a function is each x has only one y. So it's a function in which each y has only one x value. So no repeat. I'll do that over here. So what are we looking for? We're looking for x's and y's don't repeat. So what are we looking for? We're looking for the fact that we have no repeating x values and no repeating y values. But first it must be a function. So let's take a look at what we got here. We're going to see if any of these are one-to-one functions. So first we're going to decide if it's a function. If it's a function, you'll only see arrows going in one direction to one place. So it only goes to one place. Only goes to one place, only goes to one place, only goes to one place. So yes, this is a function. The question though is it a one-to-one function? So now what we want to do is we want to look in reverse. We want to see, does this y value only have one x value? Yep. Does this y value only have one x value? Yep. Does this y value, it's got two x values that point to it. So this is not 1 to 1. That's how we represent 1 to 1. This is not a one-to-one function. So let's take a look. This passes the vertical line test. It's a function. If I draw a vertical line through each one of these points, it only hits the graph once. So yes, it is a function. The -2 doesn't repeat. -1 doesn't repeat. 0 doesn't repeat. 1 doesn't repeat. And 2 doesn't repeat. Now, number 3. On the y-axis, there's only 1 point. Number 1, there's only 1 point. 0, there's only 1 point. But down here at -3, look at that. There's 2 points right there. So this is not a one-to-one function. All right, a parabola, it's an upside-down parabola. It passes the vertical line test, so it is in fact a function. But, on this -1, only 1 point. This -1.5, only 1 point. This -2, only 1 point. But let's take a look at the other way around. Let's look at the y value of 2. The y value of 2 has a point over here as well as a point over here. In fact, if you were to do those 2 points, it might be -1.5, 2. And this point would be 1.5, 2. Notice the repeating y values. So not 1 to 1. Not a lot of functions are 1 to 1. All right, let's take a look at this. It passes the vertical line test. So it is in fact a function. And let's see, that 2 only has one value, that 3 only has one value, that 3.5 only has. So yeah, this is yes. This is a one-to-one function. This is also yes, one-to-one function, right? You only see one value. Okay, so at this point I'm going to teach you about something else because I think at this point you probably already started to get an idea of it. And that's this idea of, let's take a look at first, if we want to determine if it's a function, and I'll go back to this one as well. We'll do both of these this way. I meant to do it there anyway. It passes what's called the vertical line test. So the vertical line test is going to tell us that it's a function. But then what I want to do is now I want to look at lines that are horizontal. Horizontal line test. We're going to run the horizontal line test. And if I only hit the graph once, drawing a horizontal line test, HLT, then it is if it's both of these, then it is a one-to-one function. So that's why I said here, passes the vertical. Also, it passes the horizontal line test. So yes, one-to-one. This one will pass the vertical line test. So it is, in fact, a function. But in order for it to be a one-to-one function, it has to pass the horizontal line test. And notice right there, as soon as I draw that in, it fails. So not one-to-one. Circle is not even a function, so no. Don't have to do any other work. This is a function. This is the cosine curve. It passes. But if I were to try to draw in a horizontal line, man, it hits it all over the place. So this is not a one-to-one. And yes, this is a function. Wait, let me check. Yep, see how it's open and closed, open and closed. Those are where you're going to have your problems, open and closed. So yes, this is a function. But it does pass the vertical line test. I mean, draw lines in. We can draw lines in everywhere. It passes the vertical line test. But, and this is kind of tricky, it's going to fail the vertical line test. Right there, it fails it. So this is not one-to-one. So in order to determine if it is a function, we use the VLT, the vertical line test. In order to tell if it's a one-to-one function, after it's passed the vertical line test, we look for the horizontal line test, and we look for this. Now, there's always one person, horizontal. Can I just check the horizontal line test to tell if it's a one-to-one function? Well, what if I gave you a graph that looked like this? Does this pass the vertical line test? Nope. But it sure as heck passes the horizontal line test. So it would pass the horizontal line test, but you don't even want to test the horizontal line test because it doesn't pass the fact that it's a function with the vertical line test. So you have to check vertical, then horizontal. All right. Let me take a quick break. If you haven't done so already, do me a favor, hit that subscribe button. Give me a couple more subscribers. Let your friends and relatives all know about subscribing to this amazing math channel where you can learn some math too. Oh my God, another great commercial. Inverse relations and functions. If you think about inverses really just being, I'm tired of pink, is just being opposites. Wait, is that the right word or is it OPP, opposite? I think it's opposite. Yeah, I think it's opposite. They're really just kind of opposites. Like, for example, what's the inverse operation of addition? It's just subtraction. What's the inverse operation of division? It's just multiplication. So that's what we're going to be doing. We're going to use inverses all the time in math to kind of undo each other to kind of work on problems. So if we want to look for inverses or look for the inverse of a relation, what we want to do is we want to do the opposite. The easiest way to think about this is we just want to switch x and y values. That's all we want to do. We want to switch the x and y values. So let's first of all figure out, we were given a relation here. This is a relation. Now I want to see if it's a function. I'm just curious. -3, -2, 1, and 3. So it is definitely a function because I do not see any repeating x values. Let's see if it's a one-to-one function. -2, 2, -1, 1. No repeating y value. So this is a one-to-one function. So I want to come up with, and I want to write its inverse. So the inverse of this function would look like this. What we're going to do is simply switch x and y. So -2, -3. Switch. 2, -2. Switch. -1, 1. See how we switched it? And 1, 3. There it is. That's the inverse. If it's given to you in table format, well, it's just as easy. We're going to switch the x and y's. 30, 40, 50, 60, 3.4, 5.0, 7.0, and 9.2. That's it. And yeah, no repeating x values, no repeating y values. So that's a one-to-one function. So this would be a one-to-one function. This would be a one-to-one function. Let's take a look at this one. This isn't even a function, so it sure as heck can't be a one-to-one function. But let's talk about its input, and we'll talk about the output. And we're going to do a nice mapping diagram. I'm going to do different colors, make it all fancy, get some purples in there. So I'm going to reverse the x, or switch the x and y. So I'm going to put 38, 40, 50, and 75, 0, 24, and 36. And we just draw arrows. So the 38 come from the 36. So the 40 came from the 24. The 50 came from the 24. And the 75 came from the 0. That's it. This would be the inverse. This is not even a function. So it sure as heck can't be a one-to-one function. All right. So let's talk about inverses graphically. So let me blow this up a little bit for you. Again, probably shouldn't be using those words, but that's what we're going to use. So inverses. So we're going to take the inverse of these functions. And then we're going to do it algebraically because that's just the fun part of everything. Algebraically is not too bad. So remember what I said. We're just going to switch the x and the y values. So I don't have any x and y values, so I'm going to go find some. I'm going to go find some nice points. There's a nice point. There's a nice point. There's a nice point. And there's a nice point. So this point here is the point 2, 3. So if I switch that, that would be, I don't use that. That would be 3, 2. So 3, 2. And then this point right here is 1, 1. If I switch that, that would be, well, 1, 1. This point here is 0, -1. So if I switch that, that would be -1, 0. And then this last point is -1, -3. So if I switch that, that would be -3, -1. So let me try to do the best I can drawing in my inverse here. So if this function, and let me give you a little bit of notation. I'm not sure I've talked to you about a little bit of notation yet, but I'm going to eventually. This would be f of x. And this one down here would be f inverse of x. I'll talk to you about notation tomorrow. All right, let's do another one. Inverses aren't bad. All right, there's my function. We'll do it in blue. This is my f of x. I got to find some points, so I'm going to go find some nice points. I got this point right here, get this nice point right here, and I got this nice point right here. So this point is 2, 0, so I'm going to look for a 0, 2. Now notice it's an open circle, so I got to do that. 3, 1, so 1, 3. And 6, 2. 2, and then 6 would be somewhere up here, but it's off my graph. So I still want to graph it, but I want to try to do the best I can. Something like that. That's it. Just because so it'll make my life easier, I'm just going to go down. Oh, I hate this one. I'll do that one last. Let's do this one. So this one will be a little bit tricky. Oh, by the way, this would be f inverse of x. All right, so the original function here is f of x. I'm going to go do f inverse. Now, I don't have a lot of nice points on this one. I got this one. Man, I got almost no nice points. Let's say this one is close. So it looks like we got one down here, there. That's close. And this one is kind of close. Those are about the best I'm going to do. So this point is 2, 0. So 0, 2. This point here is 1, negative 4. So negative 4 and 1, but it's a little bit above. So a little bit above 1. So there. And this point here is 4, 1.1. So 1.14. So this is going to look like, man, that's hard to do. There. And this would be f inverse of x. It's just notation. That's just how we do that. So we got one more to do. Oops, this one. We got lots of nice points here. We got all these points. Now that point is 1, 1. The reverse of that is 1, 1. That point is 2, 2. The reverse of that is 2, 2. 3, 3, 4, 4. So those points don't move. This point is negative 1, 1. So I want to do 1, negative 1. This point here is negative 2, 2. So I'm going to do 2, negative 2. This point here is negative 3, 3. So I want 3, negative 3. And this point here is negative 4, 4. So I'm going to do 4, negative 4. So the inverse of this is really this. Oh my God, I missed those points. Shoot. And so this would be f inverse of x. Now, let me back this up, and I want you to take a look at all 4 of them. And I'm asking this question. What simple reflection do you see that would go from the original function to the inverse? Does anybody see it? I'm going to use my black pen right here. It is, believe it or not, it is simply just a reflection in this line. Do you know what the equation of this line is? This line, if you look right here, all inverses are simply reflections. That's why that stayed the same, because it's on that line. That's the line y equals x. So inverses are simply just reflections over the line y equals x. That's it. All right. So remember what we said a few minutes ago. With inverses, we switch x and y. Now, what goes with x? Domain. What goes with y? Range. So, if that's true, then wouldn't the domain of f of x, if I switch x and y, aren't I also switching the domain and the range? Right? If I go back up to here, and I look at this problem right here, this is an easy one to look at. Here's a domain here. What did it become in the inverse? It became the range. So the domain of f of x is the range of the inverse. And of course, then the range of f of x becomes the domain of the inverse. So to find an inverse, we switch x and y values. To find the inverse of a graph in a relation, it is a reflection over or in the line y equals x. All right. Now we're going to do it algebraically. Oh, here's my notation. Here's the notation. This is just inverse notation. That's all you got to remember. That's the notation. All right. So, I hated this. I thought I fixed this. Anyway, so sometimes you'll see it written like this. F of x equals negative 3x plus 4. And you got to remember, oh yeah, f of x is really just y. Now, I told you a few minutes ago, in order to find the inverse, you simply switch the x and y. Well, that's what we do here. That's all we're going to do on this problem. In order to find algebraically, not graphically, but algebraically, the inverse of this function, what we're going to do is simply switch x and y. Not the numbers with them, just the letters. So this will become x equals negative 3y plus 4. So switch x and y, and then simply solve for y. So to solve for y, I'll subtract 4, so I get x minus 4 equals negative 3y. Divide by negative 3, and I want you to get in the habit of dividing each piece by negative 3. So I end up with negative 1/3 x, right? Because remember there's a 1 right here. And I never leave negatives in the denominator. So negative 1/3 x plus 4/3 is equal to y. And then I want you to get in the habit of writing an inverse notation. F inverse of x is equal to negative 1/3 x plus 4/3. Now, one of the things I would hope that you would do or get in the habit of doing is checking your answers. And you can do it very quickly on the calculator. Our original was negative 3x plus 4. That was the original function. I always put in the line y equals x because that's the line of reflection. And then I'm going to do this one. So that's control division, tab, control division, negative 1/3x plus 4 divided by 3. So this one's kind of hard to look at. But if you look at this, the red line is the reflection line. So if you look at this blue line, this line, and reflect it, it's going to be this black. This one's hard to look at. But by the way, notice that the line of reflection always goes to the point of intersection. And that's always got to be true too. Well, no, that's not always true. If they intersect, then it will be true. All right, let's look at this one. We're going to switch x and y. So we're going to put x equals 1/3 y plus 9. Now, I hate fractions, and I know you do too, so we're going to take this whole equation and multiply it by 3, because that will get rid of that fraction. So I end up with 3x equals, now 3 times 1/3 is just 1, so that's y, plus 27. Bring the 27 over, I get 3x minus 27 equals y. So my answer is f inverse of x equals 3x minus 27. And we got one last one. Switch x and y. X equals negative 1/2 y minus 3. Again, I don't like that 2, so I'm going to take the whole thing and I'm going to multiply by 2. So I get 2x equals negative y minus 6. Add the 6 over, I get 2x plus 6 equals negative y. Divide each piece by negative 1. And I get, I'm out of space, I'm out of room. I'm probably working behind my head. I get negative 2x minus 6 equals y. But do not leave it like this. I want to see an inverse notation. So f inverse of x equals negative 2x minus 6. All right, so let's just recap all the stuff we've gone through today. Vertical line tests. The vertical line test to determine what x values repeat. And that's only to determine it's a function. The horizontal line test determines where y values repeat, and that will tell you if it is a one-to-one function. One-to-one function. And what a one-to-one function also means is that the inverse will be a function. In other words, if it's a one-to-one function, the original function will be a function, and if you graph the inverse will be a function. We'll talk about that more as we go through. F of x is the notation for function. F inverse of x is the notation for inverse. Now, if I gave it to you in set notation, to find the inverse, you switch x and y. -2, 2. 0, 3. 2, 4. If I give it to you like this, you have some work to do. X equals 2y minus 13. X plus 13 equals 2y. Divide each piece by 2. So I get 1/2 x plus 13 over 2 equals y. So inverse notation will be F inverse of x equals 1/2 x plus 13 over 2. You could say 6.52. And then if I give it to you graphically, you find some nice points and you just switch them. So this point here is -1, 0. So now I want 0, -1. Let me do it in red or pink. This point right here was 0, -1, so that becomes -1, 0. And then I got one other nice point that's over here. It's 3, -2, so -2 and 3. And notice those are, in fact, reflections over the line y equals x, even though I didn't draw that line in very well. All right, that's inverses. Again, if a function is one-to-one, then not only is the function, is the original a function, but also the inverse is a function. All right, that's it. Hit the subscribe button, kids. Catch you on the flip side. Nice job today. Bye.